Hi, everybody. Good morning. My name is Marco Pettoni. I'm a scientist here at Lawrence Berkeley Lab and lead for CalFlexHub R&D projects. Yesterday, my colleagues presented the CalFlexHub projects on residential technologies and water heating technologies. Today, I'm honored to present our project on commercial building technologies. Next slide. So we acknowledge that commercial buildings are more heterogeneous and complex than residential buildings, and we want to map our projects to different segments of commercial buildings. And we like to think about commercial buildings as communities, which is a collection of buildings typically owned by the same entity and with some of the services in common, like central plants, like a university campus, large commercial buildings, and small commercial buildings. The difference being that large commercial buildings typically have built-up HVAC system and they are custom to each building, and light commercial buildings have packaged rooftop units. Next slide. This is a simple map of how our project covers different end uses that provide flexibility in the three different subsectors. So there's quite a bit of coverage, but we don't cover all the cases. Next. And this is all the areas that the California Energy Commission EPIC program covers: applied R&D, technology demonstration, deployment, and market facilitation. And next. And this is how our projects map to these areas. Today, as you can see, we have both R&D and TDD project. But today, we're not going to describe the technology demonstration deployment projects, but only 4 of the R&D projects. And the TDD project will be presented in a future seminar. Next. I think it's also helpful to understand and to show how these technologies provide flexibility, because there's a different combination of type of controls. So you can see advanced controls on the top and different type of storage. There's passive storage using the envelope of the building. There's active storage, and there's electric storage. So technology mapped to different areas and cover quite a bit of the possible combination of spaces. Now, what I want to do next is introduce my first speaker. Next slide, please. And jump directly into the presentation so you can see what we're working on. And we'll have a session at the end, about 20 minutes for our question and answers. So I'm honored to introduce the first speaker for this project called HP Flex, the next generation of heat pump load flexibility, Armando Casillas. He's a senior scientific engineering associate at Berkeley Lab.
Hello, everyone. Thanks, Marco. My name is Armando Casillas. I'm a senior SCA here at LBNL, and I'm delighted to be kicking us off here with our project entitled HP Flex, which is working to pave the way for our next generation of heat pump load flexibility. Next slide, please. All right. So California develops more aggressive building electrification and decarbonization goals, we will begin to experience a rapid electrification of our space heating loads, mainly through heat pumps. The resulting unification of our HVAC system's fuel source will result in new morning peaks on our grid and potentially higher electricity costs for customers, which further establishes a need for year-round optimization of our space conditioning loads. HP Flex, as we call it, is a platform for developing to enable optimized price-responsive heat pump systems in small to medium commercial buildings, like as Marco mentioned, make up a significant portion of the building stock and yet don't get nearly as much attention as large buildings with built-up systems. The HP Flex platform leverages Voltron, a DOE-funded middleware that essentially coordinates the communication across our architecture, pulling in pricing and weather data and pushing it to our price-responsive controls. Voltron also stores our various hardware drivers to accommodate disparate communication protocols such as BACnet, LANWorks, Modbus, and systems in order to enable the execution of our load flexible sequences. So next slide, please. This is our project team, PIs Richard Brown, Donghoon Kim, Marco Bertoni, and our technical team, Anand Prakash, Sangwoo Ham, Laszlo Paul, and myself are working on this project. Next slide, please. Okay, so the HPFlex provides optimization via a growing library of model predictive control algorithms, or MPC for short. Early this year, our team performed a series of tests at LBNL's FlexLab experimental facility. Our rotating testbed is equipped with a rooftop package heat pump unit manufactured by Aeon. A perfect first test case for us to implement a couple of different flavors of price responsive MPCs, our ideal MPC and our hybrid MPC. Both MPCs responded to a modified two-peak highly dynamic price signal with the goal of moving peak loads away from morning peak price and shift earlier to cheaper times via preheating of the space. We learned quite a bit during this initial experiment, such as the relationship between the shiftability of the building load and the responsiveness of the HVAC system. So for example, we would command the system to preheat the space to a pretty high temperature right before the peak price, but found that the space wouldn't really reach a set point and would take on the order of a few hours for the system to actually heat that space, which was further exacerbated by the stratification of the air in the space, which prevents the ideal mixing you would ideally want in a zone. Overall, though, we were able to shift a comparable amount of load with our two MPCs, about 50% of the early morning HVAC load, to avoid the early morning peak price, which was exciting given that, unlike the ideal MPC we tested, our hybrid MPC does not require direct measurement of internal load, meaning it takes significantly less time to develop and deploy. In cycle 2, we plan to develop more variations of MPC algorithms to accommodate different HVAC systems and configurations, such as thermal energy storage integrated systems, which we're currently testing in FlexLab, and variable refrigerant flow system, VRF system, all in an effort to gear up for deployment in our 6 disadvantaged community located building test sites sometime next year. A later task in this project is to take our lessons learned with contractors and sites and develop a curriculum for workforce development. On top of that, we have also coordinated with a few manufacturers, including Trane and Daikin, throughout this process, who have been really engaged and are eager to hear the result of our efforts. So with that, thank you very much, and look forward to the discussion later.
Thank you so much, Armando. This is a very interesting project. As you can see, this is looking at advanced controls using rooftop units and existing envelope of the building. So we don't install any thermal storage, you use the thermal storage capability of the building itself. Now, the next talk and project is integrated heat pump hot and cold storage for small commercial buildings. So same sector, small commercial, which is being, typically not developed as much as large commercial buildings for demand flexibility and demand response. And the speaker is Spencer Dutton, who's a principal scientific engineering associate at Berkeley Lab. Spencer, take it away.
Great, yeah. Can you hear me okay? Good, yeah. Thank you, Marco. Yeah, so I'll be talking about our next project, integrated heat pump with hot and cold storage for small commercial HVAC. This project actually follows on from prior LBL research and development into building HVAC systems that incorporate phase change material-based thermal energy storage. So phase change materials have a potential to store dramatically more thermal energy by volume than, say, hot water, roughly about 4 times. So using this thermal energy storage, we have a potential to shift a building's entire heating, cooling, and hot water energy use to lower carbon, lower cost periods. Next slide. So the CalFlexHub project that we're just talking about takes advantage of a prototype hybrid system that has this both cold and hot storage using these phase change material-based thermal batteries. They're targeting a small commercial building. This prototype is a technology demonstrator intended to be a drop-in replacement for small vertically mounted package units that are commonly used in schools, labs, like this one, LBL. On the bottom right, you can see a schematic layout of this system that's integrating an efficient air-to-water heat pump, a hydraulic air handling unit, and then 2 PCM, phase change material, thermal batteries, one for cold storage and one for hot storage. And the top right, hopefully you can see the cross section of one of these thermal batteries. These ones were developed by a company called Sunamp in the UK, but a few companies are commercializing similar modular PCM-based thermal energy storage. As I hope you can see, it's based on a metal heat exchanger that is then sort of immersed in phase change material. And then on the outside is a highly efficient insulation material. It's actually vacuum insulation that they use. So those same three components that are in the schematics there are also shown down on the bottom left in our lab. So the goal of this project is actually to develop and evaluate the controls that respond to these dynamic pricing signals, building off the other efforts in some of the other projects, to lower the energy costs and reduce the associated CO2 emissions of this system, to control more optimally the operation of when to charge, when not to charge, when to use thermal energy, or when to hold off from using that thermal energy that you have in storage. Next slide. So the team for this project include Armando Casillas supporting the hardware controls, Anand Prakash supporting the development of the controls architecture, and I'm the project lead. The graphic on the right shows a proposed field development of this system to give you some context. And that's put onto the FlexLab's office building. Demonstrating the real world performance in an occupied building is really important to the industrial partners that we've gathered throughout the prior project to enable a pathway to future commercialization efforts. Those commercialization efforts would include integrating these main components into a single packaged unit. But to be clear, this field demo is not currently planned as part of the CalFlexHub efforts. But that would be contingent on future funding. Next slide. In cycle one, we added additional temperature sensors and power monitors, and then developed the controls hardware that define the system's main operating modes. So including the ability to charge and then discharge, utilizing that thermal energy. The plot on the right shows this two-peaked highly dynamic pricing signal. The system can now switch between 9 distinct modes that it's needed to respond to these pricing signals. And we performed tests to respond to the winter and summer and swing season scenarios using operating schedules that were in this cycle generated by humans. In cycle 2, so this current cycle, we'll be focusing on developing the controls architecture and rule-based controls needed to generate those look-ahead schedules automatically. Those supervisory controls are shown here on the top left of the diagram. By the end of cycle 2, the system will be able to receive and then act on those Midas price signals, and we'll be comparing the system's performance both in terms of energy use and projected energy cost and projected carbon emissions, comparing that to the baseline control strategy that operates on a fixed charge schedule. That's it. Thank you very much.
Thank you, Spencer. This is a very exciting project with a pretty cool prototype that can both, this is interesting, both store energy and also allow for downsizing of the equipment for new equipment, which is pretty cool. And it's both for heating and for cooling. So we're going from this kind of example of storage for small commercial buildings to in another example of storage for large campuses. And this is model predicted control, so an advanced control algorithm for dynamic district energy system for renewable energy integration and grid decarbonization. That's a long title. Dong-Hoon Kim is the PI of the project, and he's here. He's going to show us what the project is about and take it away.
Thank you, Marco. Please go to the next slide. Okay, this project is talking about a existing water-based thermal energy storage, such as chilled water tank, ice storage system. Those are very classic, is old, and one of the most reliable energy storage technology. And more importantly, those are already available for many large commercial buildings and district energy system as well. The idea of this project is let's try to make a full utilization of these available resources for grid decarbonization and to meet increasing dynamic load flexibility need from the grid. Next slide, please. My name is Dong-Hung Kim, and this work is strongly collaborated with UC Merced. Jim Brugger, he's the facility manager of the UC Merced. And on the left-hand side, it is showing the schematic of what kind of a system we are controlling. So we are looking at the central cooling plant at the UC Merced that serves around 40 campus buildings. And we have 5 chillers that is about 5,000 refrigeration ton capacity and 9 cooling towers. And also we have a 2 million gallon giant chilled water tank. And in addition to that, we have around 4 to 5 gigawatt renewable energies at the campus. So those are kind of a system we are controlling. Next slide, please. Would you please click the video link, Marco, at the top? Yep. Hopefully it will show some the live demonstration.
I think Hannah has control over that.
Okay. So this is UC Merced energy management system, and on the right hand side in the middle, it's a small box, but it shows the MPC activated and deactivated. So that's above the chilled water tank, and there's a small box named LVNL remote control command. And facility manager can activate or deactivate motor predictive control in MPC. So in here, I wanted to say that this MPC algorithm has been fully integrated with their energy management system. And it's here, the light, green light button is on. That means MPC is running during this demonstration period. Okay. Please start. Would you please go back to the presentation mode? One of the points that I wanted to make for the video side is the MPC has been fully integrated into their EMS system, and it's receiving the CalFlexHub signal, and also is able to receive some of the CO2 signal as well, and change the objective function of a motor predictive control in order to optimize the performance in response to the CalFlexHub or CO2 signals. So on the left-hand side figure, it shows the experimental demonstration, field demonstration result during the cycle 1. And the top figure shows the CalFlexHub signal. And the shaded area, gray shaded area represent the high peak price period. So basically, we wanted to avoid that shaded area because it's a high peak price period. And the bottom one, the second subfigure shows the campus power. It's a net power consumption, and the state of charge, which represents the chilled water tank level. And the last one is campus cooling load and the chiller capacity behavior. So when, please click, there's some animation. Would you please click just one time? This arrow shows the when the price is high, and you can see at the bottom, the chilled water tank level is decreasing. So the state of charge is decreasing, and while turning off the chiller, you can check that the chiller was on at the bottom figure. And would you please click again? Yep. So when the electric price is low, and in addition, as I mentioned, there's a 4 to 5 megawatt solar PV at the site, MPC wanted to utilize clean energy as much as possible. And in addition to that, the electric price is low during the period in this area. So the MPC decided to try to utilize these clean energies with the cheap electric price and try to charge the tank as much as possible. That's where you can see in the arrow line. Right-hand side figure shows that the CO2 response we have performed before the CalFlexHub. So this one is compare our MPC strategy in response to the CO2 signal and with the baseline control, which is the storage priority control that is pretty conventional for this large cooling plant system. And what we have seen here is you can see the blue line, which is the response of the MPC. It actually smoothed the load profile of the campus a lot and reduced the excessive power generation, on-site PV generation that is going back to the grid. We reduced a lot. So in terms of on-site solar self-consumption, we achieved almost 100% carbon emission savings, around 10%, and more importantly, for the facility side, we achieved 10 to 15% peak demand reduction. And next slide, please. This one is my last slide. I wanted to mention that district TES, Summer Energy Storage District Energy System, could be a cost-effective and near-term solution to accelerate the grid decarbonization. Because first of all, it's because of the size. We can shift the load. Just the last example is shifting around like 2 megawatt and several hours energies only for that campus. And if we imagine that we are installing some batteries for this district energy system, the cost is really expensive, but the technology we just introduced is only updating the software. So there could be some cost developing an algorithm, but that cost should be lower than installing a additional electric energy storages for such a large district energy system. Thank you.
Thanks, Dong-Hoon. Very interesting technology. So this is the intelligence applied to storage in large campuses, and you showed a lot of potential sites in California and probably elsewhere too. So thanks for that. Moving to the next one, this is about large commercial buildings, predictive control. So similar technology, type of advanced algorithm. This is applied to single buildings, and presenting is David Blum, a computational research scientist at Berkeley Lab. Go ahead.
Hello, everybody. Thank you, Marco. Once again, my name is David Blum, a research scientist at Berkeley Lab. Marco, can you move to the next slide? Yes, so this project is focusing on basically developing an MPC controller and testing it in a large commercial building where the MPC controller responds to a dynamic pricing or greenhouse gas emission signal to control the HVAC system of the building and shift loads while maintaining comfort. And you can see in the lower right-hand corner there a diagram of sort of the concept of model predictive control. And what you see there is essentially the fact that conventional control uses scheduled set points and local controllers to maintain building operation to meet those set points in response to disturbances. What model predictive control does is it adds a system model to the control system that can predict how the system will perform over time, say a prediction horizon of 24 hours, and then combine that prediction also with forecasts of things like weather and internal loads, as well as signals that could drive some kind of performance objective like dynamic pricing or greenhouse gas emission signals. And basically the model and the forecasts and the signals are combined into an optimization problem that is solved for a prediction horizon. And then the results of that optimization problem are used to implement controls to drive the system, often in the form of set point resets throughout the building. And in this way, what you can do is utilize passive or active thermal storage within the building in a way that basically forecasts over time periods of maybe low electricity prices versus high electricity prices, and shift load, shift the times that you're cooling and actively cooling and heating to periods of low prices versus high prices. And within a large commercial building, especially if it does not have active thermal storage, as we saw in the previous project, then this is important to do the optimization so that you also can maintain comfort basically throughout the day. So we are implementing this and field testing in a building on LBNL's campus called Building 59. And we are focusing on the control of 4 rooftop units that serve offices on the second 2 floors of that building. The system itself is an underfloor air distribution system. And what we are looking to control are the supply air temperature and airflow through the rooftop units that supply basically the offices. Next slide, please. So the team includes Ettore Zanetti, a postdoc researcher who's been doing a lot of heavy lifting on the implementation for CalFlexHub, Anand, as well as Laszlo and Marco. And I also want to acknowledge basically the help and significant help from LBNL facilities staff and sustainability staff who help sort of connect the MPC and operate it with the building. Next slide, please. So in terms of progress, this work builds on earlier work that was done at LBNL, funded by the Department of Energy to implement the model predictive control infrastructure, particularly for energy optimization. And that is what you see on the right there, where there's infrastructure implemented to collect data from all of the building systems that we need, including HVAC and some electrical systems, and things like site weather. Also receive forecasts of weather and electricity prices that come from a CalFlexHub server, and then basically integrate them with the MPC, which then uses that data to learn models and perform optimization in order to set points and send them back to the building automation system. So what the project has been able to do is successfully integrate communication with the CalFlexHub electricity price server into the MPC software, as well as gain access to building power measurement data points that changed since the previous work. And the project is now doing integration testing of the MPC, basically in responding to the electricity prices from the CalFlexHub server, and intends for functional tests, basically field tests in the building to start next year. Thank you.
Thanks, Dave, for the update. So I'm gonna invite everybody to come back on camera for the Q&A session. All right. There's a few questions. One was about what type of prices we're using that I'm already addressed here. There was one about static electricity pricing. I'm not sure what that meant. So if Jeffrey is here and wants to ask directly, feel free to do so. Not hearing anything. There's one question on Voltron or not, and I'm going to sort of give a high-level answer here. And Donghong and David, please, chime in if you want. We are mostly focusing on these projects on the control strategies and the control algorithms, as opposed to the middleware to deploy the system. In the project presented by Armando, we're actually using Voltron. In the other system, we're kind of using some specialized custom implementation. Those algorithms can live on potentially any platform. So they can live on Voltron, they can live on a proprietary platform, provided by a company. And we're interested in working with some of our partners to further commercialize the intelligence on top of the middleware that provides connectivity and integration. So that's any additional things, Donghong or David?
David, go ahead.
Sure. I think I would just add that, especially in large commercial buildings, you often have a BMS system that does sort of serve the role of integrating the control across the building. And so oftentimes with optimal or advanced supervisory control, you can have the algorithms living in the cloud somewhere, and you are basically using a gateway to send set points or control to the BMS system, which is already implemented in the building, and I think serves the role which Voltron often can serve in smaller commercial buildings or medium commercial buildings that may not have a BMS system.
Thanks, David.
Mm-hmm.
That's a good summary. For the UC Merced project is more about energy management system, and the video shows the kind of displays of their BMS system, which is acting as like what Voltron is doing for small commercial buildings.
Yeah, we're basically doing supervisory control on top of whatever management platform exists or doesn't exist, and we install. There's a few other questions. One about prices, structures, etc. I don't think we can address that here. We're not focusing on how the price is formed. We're currently working without demand charges in our tests. But this is a longer discussion that we can have separately. There's a question about range of energy savings. Can anybody say something about that? If you have any data or
I just I think in my my slides I did have some solid numbers from the FlexLab test that we had conducted. It was I said 50% of total HVAC load was able to be shifted, not necessarily saved, but we did see total high 20s, low 30s percentage being able to be shifted to lower price times.
And here they ask you specifically about cost savings, and that obviously depends on the tariff.
Yeah.
And because tariffs are not defined yet, and they're part of the CPUC work, we can't quite define that, but we can define how much energy we can shift. Anybody else that has I think Donghong, you had some values there in your slides, right?
Yeah, but it is more about CO2 savings rather than a dollar savings, because this year I couldn't find a good baseline because the experiment was performed during extreme heat wave season for this cycle. So I couldn't find a good baseline. I cannot come up with a dollar savings. But one thing that I wanted to add to here is the cost savings, as Marco mentions, is very strongly depending on what is the utility price signal look like. And typical TOU rate, which has on to OPEC price ratio of 2, is not very good enough to incentivize the load shifting. You can, using an MPC or advanced control, a grid can see the savings, but there's a not significant benefit from the building owner or facility owner side.
Thank you. There's a lot of specific questions on what are the objective of the optimization and other things that I think we can spend 2 hours discussing. I would rather simply move to a question that I have in my pocket and I want to ask everybody, which are, what are the challenges? And it kind of covers a little bit of what was being asked in your technology. Who wants to go first? What's hard? Why are we, are we working on your projects? What's hard with the existing technologies?
So the question is about the practical challenges of developing and deploying advanced control, or something else?
Yeah, I think that's a good way of phrasing it.
Yep.
Dong-Hoon, go ahead.
Yes.
Then I see Spencer.
One thing is I just remember David and myself is kind of documenting that we already documented the challenges related to the field, related to the deployment of advanced controls, and there are several challenges for the advanced control. One of the major part is developing a good model, which requires a lot of labor and some expertise for doing that.
Thank you, Dong-Hoon. Spencer?
Yeah, I was going to add to what Dong-Hoon said about the challenges of controlling these various different systems that you could use in a variety of different ways. Normal heating system, there's a call for heat, your furnace or your heat pump turns on and provides comfort and warmth instantaneously. But when you have this ability to either draw from the battery or draw from the heat pump or draw from a combination of those two systems, and what rates do you want to draw from each of those? When should you be preempting that charge? That's where that time sensitive complexity gets built into it. So that's a real challenge related to the controls. Integrating all these systems, in a laboratory context, and then in something that's, approaching near commercial system, integrating anything for the first time is incredibly challenging. Experimental work is hard. That's been fun. I was having a conversation with someone the other day that is trying to commercialize energy storage technologies, and one of the major hurdles they face is just sort of the pitching of it and the convincing of potential customers. So that's a future challenge that I know that we're going to face, like making that economic argument.
Thanks, Spencer. That's very important. Dave? Yeah, thanks, Marco. I just want to add also on what Dong-Hoon started to mention with respect to advanced control, in particular MPC. I think two main challenges that I can offer. One, these algorithms take more data than I think rule-based control and basically combine data into synthesizing a control solution. And that data integration and access and quality is important for these algorithms. And I think are technical challenges found sort of throughout the building industry in terms of access to quality data. So being able to access data from a lot of different systems and maintain its quality so that you can continually run these algorithms, I think is still a challenge. And then the second challenge would be being able to develop a model that's accurate enough to be able to do the proper forecasts and do the optimization can be a challenge, especially when you're looking at the portability from one, and I'll speak in the large commercial building case, from one building to another where you might have different built up systems from one building or another. So that can be a challenge as well. And there's methods for using simplified models that are able to learn and adapt but there's still some challenges in being able to evaluate how well those really do adapt at a very large scale, say across California in all large building cases. Yeah.
Thank you. So I heard, competence and skills needed. I heard teaching the economic part of it, and I heard complexity, additional complexity. I heard data and possible problems with data. Stephanie actually asked what happens if you lose the data, and I'm not sure if the project we're running are as advanced and are looking that closely to a very practical issues like this. Probably not. And Armando, do you want to add anything to the
Yeah, and I think also to address Kevin Trin's question about gulfs, we had a bridge between a simulation environment and field implementation. I think one thing that we had to do is develop some sort of open loop perturbation testing for MPC, right? So let's say you don't have that historical data that David's talking about. When you want to implement that MPC, you need to have time to gather data, right? And that's something that I think is something we're developing to be able to scale in actual buildings in our field test sites, is finding time at appropriate times. How much time do you need to be able to perturb the system enough to gather data for your MPC to be useful and accurate, right? So that's one way we tend to address that.
Mm-hmm. Thank you. Thanks, everybody. We have a lot of questions and only 4 minutes. I just want to maybe introduce another overall question that many may ask is, these are all R&D projects. Again, I said there's other 2 projects that are not listed here in our portfolio that are more applied and have companies backing them. How do you guys, who wants to go first, think of kind of moving to the next phase and making this like a viable commercial product in the future? Wants to go first?
I have oh, sorry.
Go ahead, Armando, please.
I just I think mine's pretty quick. I think once again, going off of what Dave just said about MPC and the prerequisites for MPC, I think data availability is a big one. Being able to have a slew of controllable points and monitoring points, and in order for us to be able to get to that level in package systems, I think manufacturers need to be able to kind of standardize the communication protocols that are available out of the box, right? And right now, as some of us know, lead times and supply chain issues are already hard enough, and to have a custom unit that is able to be fully controllable is even harder. So working with manufacturers, showing them our lessons learned and making the case to potentially provide more controllability and visibility out of the box would be great.
Thanks, Armando. Spencer or David?
Yeah, I can offer some ideas here. One is improved workflows to implement these advanced control algorithms to respond to prices, particularly for something like MPC. Workflows to be able to take models that are used in building design process and reuse them in the control and commissioning process. I think workflows that enable that and then use those models also for MPC and load management, I think can be really helpful. Also, I think describing and documenting, I mean, some of the questions I see in the chat, and I apologize for not answering all of them, but there are some practical challenges with keeping, say, MPC running if you do lose data streams, or understanding what the proper frequency is for updating your MPC sort of control solutions. And a lot of these practical issues, basically documenting and almost having like design guidance, I think will be helpful with respect to that. And then just to follow on what Armando said, standardized data platforms and access and data descriptors, for instance, things like adding metadata tags to data so that an analytics algorithm can go into a system and almost automatically, or at least very easily, understand what data exists and what the data is representing to then integrate into the algorithm is helpful.
You, Dave, Spencer?
Yeah, I would agree with everything that David said there, and also add that, I mean, that's one of the challenges with this technology is sort of quantifying these energy costs and carbon savings, and energy cost savings and carbon savings, and doing it not just, you know, at the level that we're working on it in sort of the research level, but then getting that out to practitioners and engineers in the field that can use these tools to make the case for these technologies, to show to customers the real impacts. I think that's a real challenge right now, and it's not one that we don't have a great pathway to achieve.
Thanks, Spencer. Dong-Hoon, last word, and then I think we need to stop.
Yep, I wanted to add that buildings, HVAC systems, it has a kind of like a lot of variety of HVAC configuration and the controllability. So one of the challenges of scaling the model predictive control for the building is that kind of a variety. So one of the strategy could be we can group kind of a similar buildings that having similar HVAC configurations and controllabilities, and develop a model predictive control and distribute multiple building for the same group of the building type. And by doing that, I think that we could find a way of scaling those approach for advanced building control.
Thanks, Dong-Hoon. Thanks, everybody. There's still a lot of questions unanswered. We invite you to come to the session later on, where we're gonna kind of open up for questions live, or the one that haven't been answered here. Thanks, everybody, again for attending, and talk to you soon.